Hi, so in this video, we're going to analyze this common gate amplifier that's based on a JFET, junction field effect transistor. All right, so just some terms here. So we have II, that's the input current from the source, IO, that's the output current for Vout, VO. Then you have the input impedance ZI and output impedance ZO. So those are things that we have to find out. And then there's some additional things like, for example, ZS. This is the impedance seen at the source. Yeah, ZS. And then so we're going to derive ZI, ZO, AV, the voltage gain, and the current gain. All right. Okay, so as per always, whenever we're doing an AC analysis of the DC circuit, we need to do a few things. Yeah? So these are the 3 steps that we need to do. First, we need to short all capacitors. So C1 and C2 will become short. Zero all DC sources as number 2. So that means, well, the only DC sources here is VDD. So this will become 0 volts. And finally, we replace the transistor here, yeah, with an AC equivalent model. All right. Now, for the JFET, I think you saw my earlier video of doing a common source amplifier. So this was the transistor model that we used, a very simple transistor model. And so we have the source at the bottom, gate on the left, and drain on the right. Okay. So what we need is to have gate at the bottom and then source and drain as shown there. So first we need to rotate our model so that gate is at the bottom. And then we need to flip source to be on the other side and drain to be on the right hand side. All right, so let me just do a quick flip horizontal. All right, so it becomes something like this. So you have a ground at the bottom and then drain right, source left, and there's a dependent current source GMVGS flowing from right to left. So our transistor will then look something like this. All right, so that's the equivalent just like below. So let me just put this one away. So you have a gate at ground. Yeah, so the gate is connected to ground as before. On the right hand side of the device, we have VDD as 0 volts. So which means you're going to have RD connected between drain and ground, and C2 becomes a short, so something like this. All right, so you still have IO flowing up as before. And then on the left side, you have C1 being shorted, and then RS connected as shown there. So this side is quite straightforward. All right. All right. So that's the AC equivalent circuit that we're going to analyze here. I've just added a dotted line here to mean that that's the interface into ZS, the impedance seen into the source. All right, ZS. Okay, so let's figure out our usual 4 things, IO, II, VO, and VI, so that we can then work out these components up there. All right, so let's start with IO. Well, if you look at IO flows up and then goes left because this is open circuit, so it goes left and becomes GMVGS. So that means it goes around the loop and comes back. So therefore, IO is just GMVGS, right? So KCL, IO is just simply GMVGS. All right, so that's fairly straightforward. All right, so now let's have a look at the what do you call the II side. All right, now on this node A, if you noticed, there is a flow of current through RS coming down, which is a combination of II that's flowing from left to right towards this point, and from right to left, GMVGS. So you have GMVGS coming in from right to left, and an II coming in from left to right. And together they join, and they come down through RS, and then II will split back to the left, back to the source, and then GMVGS will flow to the right towards IO, towards RD, and then comes. So that is the GMVGS loop. This is the II loop. All right. All right. Well, another thing that you should notice is that the VI is pointing up. Yeah. So the plus side is on this top node here, is actually the negative of VGS, because VGS is pointing downwards. All right. So again, this is, if you like, this is KVL2. So VI just simply equals to uh, sorry, this is KVL. So VI just simply equals to negative VGS. So that's another term that we can put down. So I'm going to say KVL VI is just simply equals to negative VGS, right? Yeah, so they both share the same nodes, right? The top node and the bottom node. All right, so it's just that the signs are opposite direction, right? So VI is equal to negative VGS. Okay, so now let's go back to this part here. So again, this is part of KCL. All right, so I can write okay, so I can write the current flowing down through RS as, let me call it IRS. So, okay, IRS, all right, is equal to II plus GMVGS, right? All right, okay, and so that's what IRS is. That's the current flowing down through RS. But then IRS is also, you can describe it in Ohm's law terms. So I going through here, I equals V over R. The V is going to be VI over RS. So we can rewrite that as, yeah, the IRS is simply VI divided by RS. Okay, so that is equal to II plus GM VGS. And since we know that VI is just negative VGS, so therefore we can write negative VGS divided by RS is equal to, you know, the stuff on the things on the right hand side of the equation plus GM VGS. Okay, so we could combine VGS's together. All right, or we could, so we well, let's just rewrite this in terms of II, because that's basically what we want, right? We just want I in terms of everything else. So we can put GMVGS to the other side, so leaving just II, and then maybe I can flip the whole thing around, so I can then rewrite that as II. All right, is going to be equal to, all right, so it's going to be negative VGS. All right. Okay, I think I'll just write everything down so that I don't confuse you guys. So this is GM VGS, right? So basically, I'm just flipping the equation around, right? So that I have II on the left-hand side. So then, of course, I can group VGS just together. So that's negative VGS. So factor that out, plus GM, right? Okay. Or I can write it in terms of a common denominator. So it's going to be 1 plus GM, 1 plus GM RS, all divided by RS. Okay, so that's the equation I'm going to use. So that's for II. Okay, so you have IO equals this, and II equals that. VI equals negative VGS. So what's left is just VO. Well, VO is fairly straightforward. VO is just Ohm's law, right? So V equals IR, I being the current passing through RD, and then R being RD, right? But since we want VO to be positive pointing up, then we need an IO current that is flowing down, all right? So this is just Ohm's law. So I think okay, I'm going to run out of space here, so I'm going to just put Ohm's law over here. All right. And basically VO is just simply negative IO. Yeah, we need to have IO flowing in the other direction times RD. All right. And we know what IO is. IO is GM VGS. So we can just write GM, negative GM VGS times RD. Okay. Okay, so we have the 4 bits, IO, II, VI, and VO. So let's work out our 4 components. All right. Just wondering if I'm going to run out of space or not. So let me see. Can I just go up a bit? Oh, yes. Okay. Okay, so, all right. So let's work it out. So ZI, the first one. Now ZI is going to be, okay, sorry. We need to work out what ZS is. I think that's the first thing we need to work out. Because we need to use it for ZI, because basically ZI is going to be the parallel of RS and ZS, right? So let me just write that down with ZS, right? So we need to find out what ZS is. Okay, so let's see what ZS is. Well, ZS is going to be again using Ohm's law. R equals V over I. V being VI, okay, over I. I is going to be IS. I've not labeled here. So imagine that there's an IS flowing from left to right. That means IS is flowing into the source, and IS, all right? Let me just label IS up there. All right, so I've labeled a current going into the source as IS, okay? So let's have a look at, as I said, ZS is going to be using Ohm's law. So this is again using Ohm's law. So I'm going to continue from here. ZS, all right, is R equals V over I. So V is VI over R. Sorry, over V over I is IS. Sorry, yes. Okay. Okay. So, well, we know what VI is. VI is just simply negative VGS. So let's put that down. Okay. But now, what is IS? Well, IS is the same current that is GM-VGS. It's just that it's on the same node. So it's in the opposite direction. So therefore, IS is simply negative GM-VGS. All right. So the negative cancels out. VGS also cancels out. So therefore, what's left is just 1 over GM. All right. So let me just show that canceling out business. All right. So then what's left is, well, negative negative becomes positive. So ZS is just 1 over GM. Okay. All right. So now that we have ZS, so therefore ZI, right, is simply RS in parallel with 1 over GM. Oops, I think I'm using that symbol incorrectly. Hang on a sec. 1 over GM. All right. So that's our ZI. Okay. Now let's have a look. I'm just going to put over here for ZO. Let's have a look at ZO. As always, whenever we do ZO, we need to zero VI, right? We need to zero the input source. So, so when VI equals 0, okay, if you look at our equation for VI here, so if VI equals 0, that means VGS is also 0 because they share the same node. So if VGS is 0, then GM VGS is also 0. That's 0 amps, meaning that this is now an open circuit. So that means the only resistance or impedance seen from VO, i.e. ZO, is just RD. So ZO is quite straightforward. ZO is just simply equals to RD. All right. Okay, so now let's have a look at the next part, which is AV. All right, so let me just, maybe I can put it over here. All right, so what is AV? Well, AV is defined as VO, that means output voltage divided by input voltage, VO over VI. All right, we have expression for VO, that's this here, right? And VI is just simply negative VGS, if you remember. Negative VGS, right? So therefore, the VGS comes out, the minus becomes plus, the 2 minus becomes a plus. So then what's left is just GM RD. Okay, so that is AV. Now looking at AI, we can do a similar thing. Let me just adjust this a bit so that I'll just continue writing on the right hand side. All right. Okay, so here I'm going to write for AI. Now AI is defined as the output current divided by input current. Oops. All right. So again, we have expressions for those. IO is just GMVGS divided by II. So I is slightly longer expression. This is II. All right. So obviously a few things cancel out. VGS, well, actually only VGS cancels out. Okay. So leaving a, so there's a negative here. So an RS goes up. Okay, I think I'm gonna need a bit of space here. Hang on. So so it's gonna be negative. All right, and then the top part will be GM times RS. All of that divided by 1 plus GM RS. It doesn't fit. So let me just adjust this a bit. Okay. All right. So that's the equation, the 4 equations that we were looking for. So Zi is just RS parallel with 1 over GM. ZO is just simply RD. The voltage gain is GMRD. And the current gain is negative GMRS over 1 plus GMRS. All right, thanks.